Yes, I have started recording. You can start.
Okay. So welcome to the 6th lecture on this classical Lego. So in the previous lecture, we have seen that OP, Q has 4 connected components and SOP, Q has 2 connected components. Now in the today's lecture, we will really determine precisely what are the connected components of OP, Q and SOP, Q. Okay. So small observation is there. So observation. See, this is the definition of OP, Q is set of A belongs to MP plus QR. So the A transpose I P, Q A is equal to I P, Q. Observation: let A be a let A be a diagonal matrix. So that this is something like lambda 1, lambda 2, lambda P plus Q, and lambda I is equal to plus minus 1. Okay. So it is a diagonal matrix where diagonal elements are something plus minus 1. Then since A is a diagonal matrix, A is equal to A transpose. Okay. And since the diagonal entries contains only plus minus 1, so it is clear that also A square is equal to identity. Now if I look at A transpose I P comma Q A, so this is since A transpose is equal to A, so A I P comma Q and A is a diagonal matrix, I P comma Q is a diagonal matrix, A is a diagonal matrix. So these things will commute with each other. So that will give me A square I P comma Q, and A square is equal to identity into I P comma Q. So that will be I P comma Q. So that means A belongs to O P comma Q. So what I have proved that A is a diagonal matrix where diagonal elements are either plus minus 1. So that means A belongs to O P comma Q. Now in the last lecture I have proved something like proposition. This proposition I have proved. So I take an element G, so belongs to, suppose I partition this matrix GS star star G tau. Okay, and this belongs to suppose OP comma Q, and GS is a P cross P matrix, and G tau is a Q cross Q matrix. I have shown that then determinant of GS mod of determinant of GS is greater than or equal to 1, and determinant of G tau is greater than or equal to 1. Okay, so remember this fact, we will use this thing. Okay, and remember this observation also. So now I want to really write 4 sets, and we will see that those 4 sets are precisely the components of O P comma Q. So O plus plus P comma Q, this is equal to G belongs to O P comma Q. So that determinant of GS, this is greater than or equal to 1, and determinant of G tau GT greater than or equal. This is plus plus, so therefore I am taking plus 1 plus 1. So similarly O plus minus P comma Q, this is will belong, G belongs to O P comma Q. So that determinant of GS, this is greater than or equal to 1, and determinant of GT, this is greater than or equal to minus 1. Okay. So similarly, this O minus plus P comma Q, this is equal to G belongs to O P comma Q. So that determinant of GS, this is less than or equal to minus 1, and determinant of G tau, this is greater than or equal to 1. So now this is something like O minus minus P comma Q, this is equal to G belongs to O P comma Q. Yes.
OP minus, you have to change determinant of G tau. It's lesser equal to that. In the
Oh, yes. Thanks, sir. Actually, I did some wrong thing. Okay, thanks. Okay. Determinant of G is less than equal to -1, and determinant of GT less than equal to -1. Okay. So now the by previous proposition. Position. Okay, so O P comma Q. This is equal to O plus P comma Q. Disjoint union O plus minus P comma Q, and this is disjoint union O minus plus P comma Q, and disjoint union O minus P comma Q. Okay, so now one can see that each of the sets mentioned above are non-empty, and clearly this I, okay, this belongs to identity element belongs to O plus P. This is not thing. Okay. Now if you take I2 tilde is equal to diagonal of this is 1 and last entry is -1. This belongs to OPQ by observation. Okay, I have shown that if diagonal elements contains 1 and -1, then it is belongs to OP comma Q. But observe that this will belong to O plus minus P comma Q. Okay. So similarly, I3 tilde is diagonal of this is equal to -1 dot 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 1. This belongs to O minus plus P comma Q. This I4 tilde is diagonal of -1. Last everything is 1 and last thing is -1. This belongs to O minus P comma Q. Okay. So these sets are basically non-empty. Okay, now observe that if you multiply I2 tilde with O plus P comma Q, then you will get this O plus minus P comma Q. So I3 tilde into O plus P comma Q, this is O minus plus P comma Q. Okay, and I4 tilde into O plus P comma Q, then you will get O minus P comma Q. That means, and this matrix multiplication is a continuous function, and from these three lines, you can conclude that all the sets mentioned above are homeomorphic to each other. Okay. So this is the thing. Now I want to conclude that these are precisely the components of so-called OP comma Q. Okay. So now next proposition is something like that. Okay. So proposition. The OP comma Q are precisely O plus P comma Q, O plus minus P comma Q, O minus P comma Q, and O minus P comma Q. Actually, you remember always we are assuming this P greater than equal to 1, Q greater than equal to 1. Okay, and another thing is, if you really see the last exercise of this previous class, I have told you that if something is a manifold and that is connected, that means it becomes a path connected. So once I really prove that these are the connected sets, and that we are in manifold situation, that means these are also path connected sets. Okay, so you don't need any extra effort to show something is path connected in the manifold setup. Okay, so proof. Okay, so let G is equal to OP comma Q. We already know already know that G has 4 components. You already know this. Components. Let G is equal to C1 disjoint union C2, disjoint union C3, and disjoint union C4, where Ci is Pi, I is equal to 1, 2, 3, 4 are components of G. Okay, we already know. We also know that G is equal to O plus plus P comma Q. It is, we also have the O plus minus P comma Q, O minus plus P comma Q, and O minus minus P comma Q. Since G going to determinant of GS and G going to determinant of GT, this map are continuous on G. So observe that if C is any component, if C is any component, C can contain exactly one type of element out of 4 types of elements belonging to this O plus plus P comma Q and O minus minus P comma. I have explained this logic before, that suppose if C is any component, my claim is C can contain exactly one type of elements out of 4 type of elements belonging to O plus plus PQ, comma O plus minus PQ, O minus plus PQ, and O minus minus PQ. Suppose C contains 2 types of elements, something like from O plus minus and O minus plus. Suppose it contains. Then you look at the map G going to determinant of GS, then that will give a separation. Okay. So, and this is I have explained this thing precisely in the previous lecture. Okay. So that means so without loss of generality. So okay, let us use a free space. Without loss of generality, we may assume this O plus plus P comma Q. This is contained inside C1, and O plus minus P comma Q is contained inside C2. O minus P plus P comma Q is contained inside C3, and O minus minus P comma Q this is contained inside C4. Since C1 can only contains only elements of O plus plus P comma Q, and it is trivially, this also implies that C1 is also inside O plus plus P comma Q, and this also trivially implies that C2 inside O plus minus P comma Q, and C3 this is O minus plus P comma Q, C4 contains inside O minus minus P comma Q. Hence we get this equality. C1 is equal to O plus plus P comma Q. C2 is equal to C3 is equal to O minus plus P comma Q, and C4 is equal to O minus minus P. So this is, so is this clear, Tapendu?
Yes, Manoj.
Yes. So this is clear. Okay. So now, so we have proved that we have found that what are the connected components of O, P, comma Q. Now, so I to take this determinant map from O minus minus P, comma Q. I have shown that in the previous lecture, if something is belongs to O, P, comma Q, then determinant is either plus or minus 1. So it's so it will land inside plus minus 1, plus 1 and minus 1. This is a continuous map. Is a continuous map, and since this O minus minus P, comma Q is really connected, so I will get that determinant of this is a constant map. That means the determinant whole O minus minus P, comma Q is constant. Okay, you understand this meaning, but this means that it will take whole set O minus minus P, comma Q to a constant. Now as diagonal of minus 1, this minus 1, this belongs to O minus minus P, comma Q, and this this has determinant 1. So this implies determinant of, okay, so this, so determinant of O minus minus P, comma Q is equal to determinant of diagonal of minus 1 something minus 1. This is 1. Okay. So what I am getting? I am getting O minus minus P, comma Q. I am getting this is SO P, comma Q. Okay. Similarly, okay, so this is the thing. Similarly, we get this O plus plus P, comma Q inside this SO P, comma Q, and O minus P, comma Q is this is contained inside O P Q minus this is A belongs to O P, comma Q. So the determinant of A is minus 1. Determinant is minus 1. This is the definition of O P Q minus, and O plus minus P, comma Q. This is contained inside O P Q minus. Okay, so now I get what from this first thing, O minus minus P, comma Q contained inside SO P, comma Q naught. So and O plus, so I get, so thus I get SO P, comma Q is equal to O plus plus P, comma Q disjoint union O minus minus P, comma Q. Okay. So this is connected, and you know also use this fact that SO P, comma Q has two connected components. From there you can conclude that these are precisely the two components of SO P, comma Q. So proposition the two connected components of SOP, comma Q are precisely O plus plus P, comma Q and O minus minus P, comma Q. Okay, so we have proved this thing. Now I use a notation. Notation is something like this is SO not P, comma Q. This will use that one. This is the permitted component of identity. Identity in the group O. The group O P comma Q. Oh, sorry. SOP comma Q. So by this I will get that what SO not P comma Q is O plus plus P comma Q. I will drink little water. Now I will finish this pseudo-orthogonal group by giving you an exercise. So exercise. So that O plus plus 1 comma 1, this is equal to set of all matrices of this form 1 plus b square b so that b belongs to R, and this is same thing as you can write cos hyperbolic t, sin hyperbolic t, t belongs to R. Similarly, O plus minus PQ is equal to your 1 plus b square b minus p minus of 1 plus b square. This is a very simple exercise, simple calculation. So cos st sin st minus sin st
You mean
minus
1
cos. Sir?
O plus minus?
Is there any wrong thing? See the thing first diagonal entry has to be greater than 1. This is 1 plus b square. And
You mean O plus minus 1 1 is this?
O plus minus, oh sorry sir. Yeah. Yeah. O minus plus 1 comma 1 is equal to minus of 1 plus b square b. Okay, so this is my 1 plus b square. Okay. This is equal to minus of cos st sin st. So minus sin st and minus cos st. So this is last thing, O minus minus 1. This is equal to b. So this is equal to that t belongs to R. So this finishes the pseudo-orthogonal group part, and then you want to move to the other groups. So now okay, so now O and C. This is the complex orthogonal group. So take here actually our vector space, let ZW belongs to Cn. Sorry. belongs to Cn. This is the orthogonal from BZW is equal to I is equal to 1 to n ZIWI. And the corresponding matrix is identity matrix. It's equal to your identity matrix. And here, with respect to the standard basis, U1, U2, N. So ONC is something like A belongs to MNC. So that B of AZ AW is equal to B of W or to Cn. This is A belongs to MNC, B of AEI, and less than equal to I, less than equal to J, less than equal to N. So this is A belongs to MNC. So that A transpose A is equal to identity. Now SONC, you define that A belongs to ONC, so that determinant of A is equal to 1. Okay. So clearly this ONC and SON comma C, these are really pseudo-algebraic groups. So now what I want to do is see, this thing is compactness. Okay, for n is equal to 0, this ONC n is equal to 1. Sorry, n is equal to 1. This O1C is equal to your plus minus 1. So and SO1 comma C, this is equal to plus 1. So I will not now onwards will assume n greater than equal to 2 onwards. Okay, this is our standing assumption. Now these groups are actually non-compact groups. Okay, so now so first thing is SO2C is non-compact. Okay, so this is my claim. I should have taken. So this is SO2C is non-compact. I take this let AK, I will take this. So 1 plus k square ik, this minus ik, this is 1 plus k square. K belongs to Z. Okay, so actually, yeah. So if, as I've said, that you have to really always use this second condition. This is a very convenient to use. So if you use that, then you can see that this AK belongs to SO2C. So check that. Check that SO AK belongs to SO2C. This is the exercise. Okay? You use that second condition. So now as AK, so that K belongs to J. This is a subset of SO2 comma C. So and this is unbounded. So this implies this SO2C and O2 comma C are these are non-compact. So for this is for n equal to 2. For n greater than equal to 2, I use the same kind of particle. Let's see k is, I will put ak here, and rest of the thing I will put identity, and rest of the thing is 0. So this you check that this belongs to SONC. Okay, and here k belongs to Z. Now as ck, the k belongs to Z. This is unbounded. This implies that both SONC and ONC are non-compact. Okay, so this compactness we have done. We want to really move towards connectedness, and for connectedness I have to use this polar decomposition theorem, and to use that polar decomposition theorem, that we have to first show that this ONC and SONC are closed under conjugate transpose. Claim A belongs to ONC, that implies A star belongs to ONC. This is also easier thing. So as A belongs to ONC, okay, that implies A transpose A is equal to identity. So that this will imply A is equal to A transpose is equal to identity. So I will take bar in both sides. So A bar, A transpose bar is equal to identity. Now A bar is nothing but, you can check that A star transpose, and this is A star. This is equal to identity. So this implies A star belongs to ONC. Okay. So this is clear, and similarly now so now as determinant of A star is equal to determinant of A transpose bar is equal to determinant of A bar, it is also clear that A belongs to SONC. This implies A star belongs to SONC. Okay, so this is the thing. Okay, now I have to determine the connected component. I have to first prove. Sorry, I want to really take ONC intersection UN, right? Okay. So proposition. Okay, so ONC intersection UN is nothing but ON. This is okay. So proof. So A belongs to ONC. That means this is if and only if this A transpose A is equal to identity. Now, so similarly, what do you mean A belongs to UN? That will imply A star A is equal to identity. I write A star is like A bar transpose. Okay, I call this first 1, I usual 2. Okay, so this is my thing. Now if A belongs to intersection and ONC intersection of UN, then A will satisfy both 1 and 2. Okay, now take a closed loop towards equation 1 and 2. So that will give me this, since A is the multiplier in the right, if A belongs to ONC intersection UN, so that will implies Okay. Are you there, Prita? Prita, is anybody there or?
Yes, Manoj, go ahead.
Yeah.
Oh,
Yes, we can hear you.
I thought. Okay, I thought my internet connection was gone also. Okay, that's
It
good.
was interrupted for a minute.
Okay, call this as 3. Okay, so A is a real matrix, and from 1 and 2, if you put that, okay, so that from 1 and 3, we get A belongs to ON. Okay. Now similarly, if A belongs to ON, clearly it satisfies clearly A satisfies 1 and 2, and therefore thus A belongs to where ONC intersection UN. Okay, so I have proved this proposition. So this finishes the proof of this proposition. So that means it has ON has this has two connected components. So this implies so we get this implies ONC has two components. My previous proposition. Okay. Now second proposition. What was SO NC intersection UN? This will be SO, and this is very similar thing. So if okay, if okay, let A belongs to SONC intersection UN, that implies A belongs to ONC intersection UN, and this is ONC intersection UN. I have proved that this is UN by previous proposition. Now, as a determinant of A is equal to 1, this implies A belongs to SON. Okay. Conversely, if let A belongs to SON, so this implies A belongs to ON, and ON is nothing but ONC intersection UN. Okay, by previous proposition. So now, as determinant of A is equal to 1, this implies A belongs to SONC intersection. So this finishes this proof of this thing. Now, so this SON is connected. So that will give me, this implies thus SONC is connected by previous proposition and polar decomposition theorem. Proposition and polar decomposition. Okay, so now what is ONC minus, say, this is a definition, this belongs to A belongs to ONC, so that determinant of A is equal to -1. Okay, let I tilde, this is my definition, let ONC minus is equal to A belongs to ONC, so the determinant of A is minus 1. Let I tilde is equal to diagonal of what 1 1 1, rest term is minus 1. So you can check that ONC minus is equal to I tilde into. Now as this is connected and matrix multiplication is continuous, this implies ONC minus is connected. And I have proved this thing that ONC has two connected components. Now, so ONC is I have to given you an yeah. Yes, some. So ONC is equal to SONC disjoint union ONC minus. Okay. And this is connected. This is connected. So from here I will conclude that the connected components of ON, C are precisely SONC and ONC minus. So this finishes about this complex orthogonal group. Now, okay, so now I have asked a question in the previous question classes. I would ask a question to you. Why don't you? Why the books do not talk about? Don't talk about OP, QC. Okay. So Pritam, did you give any thought to it? This question?
No, I have not.
Okay, so this is actually this really requires a little bit understanding of bilinear form. So let me do that, and this is a very conceptual question. Okay, so let us give some discussion. So let V be a non-degenerate bilinear form on a n-dimensional vector space over field K. Vector space V over field K. Now I really form this automorphism group. This is equal to something like A belongs to, let's write T. T belongs to endomorphism of B over K, so that P of TU, TP is equal to B of UB for all UB belongs to B. Now I let S1, okay, so it's equal to V1, V2, Vn, be on ordered basis of basis of B. Okay. Now I form the okay, so let's say I form the matrix corresponding to bilinear form corresponding to the bilinear form with respect to the basis. Okay, how do I okay, so there the page ends here, sorry. So let us say okay sorry. Okay, so the matrix I corresponding to the bilinear form. Okay, so how does one forms this matrix? Okay, so I really take this Aij. Okay, so B of Vij. Okay, and this matrix is nothing but Aij, AB. Okay, so let us modify this. Let A denotes let A denotes the AB denotes the matrix corresponding to the bilinear form with respect to the basis S1. Okay, and how this matrix is formed? At Aij, I take B of Vij, and AB is equal to Aij. Okay, so 1 less than equal to I less than less than comma j less than equal to I. Okay, and by this matrix, by this basis is S1, I really get an isomorphism G to K to the power n. Now I realize this group ought P inside the subgroup of inside the set GL and K, right? Okay, so what I'm saying that if you really via this basis, I realize this automorphism B inside a subgroup inside the GL and K. So what it takes some form ought S1 of B is this is basically P belongs to GL and K or M and K. M and K, so that T transpose AB T is equal to AB. Okay. Now, and this group actually depends upon the choice of basis. This
What is
matrix
S1? What is S1?
S1 is an ordered basis of B.
Okay.
So I am saying that if you fix this basis as S1, then B will be isomorphic to K to the power n. This automorphism of B you can identify as a subgroup of GL and K. Okay, and that subgroup depends upon the choice of the basis S1. Or S1B is equal to T belongs to M and K, so that T transpose AB T is equal to AB. Right? Is it clear, Manoj?
Yes.
Okay, so now question. So suppose S2 is another basis B1 prime, B2 prime, and Bn prime is an another order basis. Now question I form S2B. Okay. Now question is what is the relation between ORT S1B and ORT S2? Okay. So this is the question. An answer you can expect answer you can guess this, and answer is there will exist. So these are conjugate bases. There will exist G belongs to GL and K, so that ought S2B is equal to G ought S1B G inverse. This will be conjugate, and you can expect this also. And this comes from the little bit of this is a easier exercise you can take, or if you
Is
have
that G the basis change matrix? Or
yes
something else?
yeah, it is related to the basis change matrix.
Not exactly, right? It is related.
Not exactly. Exactly, it will become, but either here it will be G or G inverse, something will become. Means that. Okay, so this is the basis change matrix. Okay, you can take it as an exercise. Okay, easier exercise, or if you have already know about bilinear form, then you can do that. Okay, so now let us apply this to our situation. Okay, so okay, so let ZW belongs to CP plus Q. Okay, first I will take S1 as our standard basis. E1, E2, this EP plus Q is the standard basis. Okay. Now I will denote this for B, P, comma Q. This index is necessary. B, P, comma Q, Z, W is equal to I is equal to 1 to P, Z, I, W, I minus I is equal to 1 to P plus 1, Z, I, sorry, P plus 1 to P plus Q, Z, I, W, I. Okay, this is B plus B, P, comma Q, and corresponding matrix with respect to basis expanded matrix with respect to basis S1 is your IP comma Q equal to IP comma Q. Now what is ought S1 B P comma Q? This is we have say that this is A belongs to M and C, so that A transpose I P comma Q. Okay, let us write T here. Okay, okay. I hope it will you will not confuse, because I have in the previous thing I have written that the corresponding matrix as A, but here actually I P comma Q I am writing. Okay, so this is my ought S1 B P comma Q. Okay, so this is one basis. Okay, and this is by definition this is O P Q C. Okay. Okay. So now put S2 actually I will take S2. I will take first P elements as it is, means P elements of the standard basis as it is. So E1, E2, EP, and second after P plus 1 I will multiply just I into EP plus 1, I into EP plus 2, I into EP plus 3. Okay, I will take the first P elements of the basis, the standard basis, and the last Q elements I will just multiply I. So let us, I will just write this as W1, W2, WP, WP plus 1, WP plus 2, WP plus Q. Okay. Now, so the thing is, okay, so what is Wi? Wi is equal to lambda I EI, where lambda I is equal to 1 for 1 less than equal to I less than equal to P, and lambda I is equal to I for actually I better to write lambda J, because I will get a confusion. Lambda J easy. Sorry. So lambda J. So lambda J is equal to I for J greater than equal to P plus 1. Okay. Now I want to form the corresponding matrix. Okay. Corresponding matrix corresponding to Vp plus Vp comma Q with respect to the basis S2. I want to really is okay. I want to really calculate that. First, I have to B of Wj and Wk. So Wj is equal to your lambda j is P comma Q. Okay. So B P comma Q. Lambda j is j into lambda k. Okay, so that will give you bilinear form lambda j lambda k B P comma Q E j E k. Okay, so and so you will get that if j not equal to k, P comma Q Wj Wk is equal to 0. Okay, and you will get also B. You will get also B P comma Q Wj is equal to 1 for all j p comma. So you will get the diagonal elements 1 and other star is 0. So the corresponding, you can check that actually this because since in the latter half actually I have multiplied this I because of I, that would be I square is equal to -1 and B of EP plus 1 and EP plus 1, this is -1, so that will give you +1. So you will get here the corresponding matrix is identity matrix. So the corresponding matrix is identity matrix. Okay. So now your ought S2 BP comma Q is equal to, with respect to this basis, A belongs to MNC. Since this matrix is identity, this is A transpose A is equal to identity. So this is equal to O n comma C, and O n comma C, this is ought S1. Okay, O n is here P plus Q, sorry. N is here P plus Q. This is by this is O P plus Q C. Ought S1 B P plus Q 0. I did it here. You write here. Actually, N is here P plus Q. Yeah. Okay. So this is the thing. So we have changed. If you take the bilinear from B P comma Q, and if you form ought S1 B P comma Q, then on one hand you get O P comma QC, and if you change the basis slightly, then you get this automorphic group OP plus QC. So by our discussion, there will exist okay, G belongs to GL P plus QC, so that
No.
yes,
Hello.
yes,
What this notation plus Q comma 0?
B P plus Q. This okay. You
Comma
take
0
this
means?
B P 0. Put Q is equal to 0. It will.
Oh, sorry. Okay. Not big. Fine.
This is okay.
Yeah, it's okay.
Okay, there will exist G belongs to GL P comma C, so that ought S2 What I'm saying? Oh, Q is equal to G ought S1 P PQ G inverse. Okay. My ought S2 B P comma Q is O P cup plus Q C G O P comma Q C is inverse. So I am getting what? This OP comma QC is a conjugate of OP plus QC. So that means these groups groups OP plus QC and OP comma QC have a similar geometric and lead theoretic properties. Geometric and topological properties. For that reason, okay, this I do not really talk about OP comma QC. Only we talk about OP plus QC. Okay, so is it clear, Riju?
Yeah.
Okay, so this is a really thing, but the story doesn't end here actually. Okay, so what I am saying that if you little bit of this, if you look at this expression, little thing, then you really see that if you change the basis little bit, this bilinear form BP comma Q is transformed to BP plus Q comma 0. Okay, so in the language of bilinear form, these are really called the bilinear forms are equivalent. Okay, these are this BP comma Q and B plus Q comma 0 are equivalent. And there is an interesting result in the complex vector space. If you take non-degenerate symmetric bilinear form, there will exist one bilinear form which is non-degenerate and symmetric up to equivalence. Okay. So what I'm saying, on the complex bilinear form, there will precisely exist one non-degenerate symmetric bilinear form up to equivalence. Let me make this precise so that you will get that thing. Okay. So okay, let me go to the next page. And there is a very difference between this real number. There is slight difference between real bilinear forms and complex bilinear form, because in the complex phase -1 is a square, and actually that really gives that uniqueness. There is up to equivalence. So what I'm saying, okay, so let me write that, then you will understand. Okay, so definition. Okay, so let V and W be two complex finite dimensional vector spaces. Let B1 and B2 be two bilinear forms on. Okay, so V and W respectively. Actually, I do not need this complex vectors dimensional. E2 little bit change here. Finite dimensional vector space over K, over field K. We will take this K is either R or C, but this definition is more general. Let B1 and B2 be two bilinear forms on B and W respectively. We say that B1 and B2 are equivalent if there exists a vector, there's an isomorphism. This is isomorphism means vector space T from B to W, so that this P to TU TB, this is equal to B1 of UV for all B belongs to. Okay, this definition is more natural. Take some time to understand this. Okay, so let B1 and B2, two bilinear forms on B and W respectively. We say that B1 is and B2 are equivalent if there exists an isomorphism T from B to W, so that U2 of TB is equal to B1 of UB for all B belongs to B. Okay, so there is a theorem related to this bilinear form. This is let B be a n-dimensional complex vector space equipped with a non-degenerate symmetric. Symmetric is important here. Okay, so if you change this symmetric, then story will change. The symmetric bilinear form be on it. Then there exists an ordered basis S is equal to B1, B2. So B, so that B of Vi Vj is equal to delta I. So I1 okay. Okay, so proof actually you can see this in the Huffman Kujeb and linear algebra. Pramath, is the statement is clear, Pramath?
No, what are you saying this? Then this matrix corresponding to this bilinear form would be identity matrix, right? If
Yeah.
I'm not wrong.
Yeah, that will be identity matrix. That was how. Okay. So let me write the next statement, then you will be clear. Okay. That's precisely the identity matrix. Because of -1 is a square here. Okay. So I will write that remarks. Okay. So let me write the remark. The previous theorem says that up to equivalence there will exist precisely one symmetric non-zero form on a complex vector space of a given dimension. Okay, so this says same if second remark, if S V B as in the previous theorem. Then ought SB is equal to your ONC. Then the ONC is the thing is, if you take that identity matrix, then the group what you get, this is ONC. Okay, and this is the second remark. Manoj, is it clear?
Yeah.
So this is about the bilinear form, about this complex on the complex. This is all about this. This is about the bilinear form, symmetric non-degenerate bilinear form on complex vector spaces. But we have an analog for real vector spaces. Actually, I was trying to avoid sort of that thing, but one of my friend Pramod here asked that, so I will write that, and that will clarify something more. Okay, so definition letter. Okay, analog. Actually, these are some standard result on this bilinear form. Analog for real symmetric bilinear form. Okay, so the thing is, I define actually. So let B be a n dimensional vector space over R. Let B be a non-degenerate symmetric bilinear form on it. Now define this P is equal to W subspace of B. Okay. So maximum of dimension of W. So the W subset of P, and the B restricted to W is positive definite. Okay. Now this Q is equal to maximum of dimension W subset of P, and B restricted to W is anybody asking something? Okay. So Q is equal to maximum of dimension of W, so that B restricted to W is negative definite, and this P Q and comma Q is called signature of the bilinear form, called signature of the bilinear form B. And since we are assuming since B is non-degenerate, okay, so P plus Q will be N. Okay, this is okay, so the theorem is something like this. Let P be a non-degenerate symmetric. Symmetric is important. Bilinear form of signature P comma Q on a real vector space V of then, since I am assuming this is non-degenerate, the bilinear form, that therefore dimension will be P plus Q. Then there will exist a basis, okay, unordered basis. Basis S is equal to B1, B2, BP, and BP plus 1, BP plus Q, such that B of Vi Vj is equal to 0 if I not equal to 0, and B of Vi is equal to 1. So if 1 less than equal to I less than equal to P, and B of Vi is equal to -1 if P plus 1 I less than equal to P plus Q. So you can also find the proof in Hoffman-Kunze. Okay, see Hoffman-Kunze. Kunze linear algebra. Okay, so linear algebra. So and so I want to really make 2 comments, 2-3 remarks. So then I will finish. Okay, I will take 3-4 minutes remarks. First remark I will take that the similar thing, the above theorem say that up to equivalence there is precisely one symmetric non-degenerate bilinear form of signature P, Q exists in a real vector space of dimension P plus Q. Now the above theorem say that up to there is precisely one symmetric non-degenerate bilinear form of P, Q exists in a real vector space of dimension P plus Q. Actually, English is not that accurate. I see that you can make it precise. Okay. So second thing is if S, V, B are as in the previous theorem, the corresponding matrix, the matrix corresponding to B with respect to basis S is IP, Q, and what S B is your O P, Q. So this is this completes actually okay. So these are precisely all the classical groups OP, Q. If you are really considering symmetric non-degenerate bilinear form or over R. Okay, so observe that in view of this theorem, and this theorem, this complex case, and the real analog of this theorem, which I have stated just now, we have really considered all the classical proofs which comes out of non-degenerate symmetric bilinear form over R or C. Okay. So, and tomorrow onwards, means next class onwards, we will start discussing about this automorphism groups which comes out of Hermitian forms, and the symplectic group, and anti sp2nr and sp2nc. Okay, so with this I would like to stop, and if there are any questions, I will be happy to answer it.
So this SLNR or SLNC, those come into which category?
These are matrix Lie groups, but we don't call those as classical Lie groups, because I gave a definition there. These classical Lie groups which comes out of this automorphism group of this something bilinear or sesquilinear form. Usually people take the connected components also. So this SLNC and SLNR, this doesn't form. This doesn't come out of this bilinear form.
But these groups are relevant, right?
These are relevant. I have discussed those things. SLNC, SLNR. I have discussed that SLNC is non-compact and
Yes.
SLNC is connected. You have forgotten, it seems.
No, I'm slightly surprised that these are not called classical Lie groups.
Yeah, people actually there in the book you will not find exact definition of classical Lie group. They will make some section and they'll start defining some group.
Yes, sir is saying something.
Let's call them neoclassical groups.
Neoclassical group.
I mean, if you like, you can call them neoclassical.
Okay, neoclassical. So, is there any question? Just one. Sir, Swagata Roy sir and Muruganandan sir and Thangavali sir, is it possible to see you?